Welcome to this ROMEO training pill from data integration to automated advisory statements. My name is Moritz Gräfe. I'm a consultant at UPTIME Engineering. We are a technical consultancy specialized on reliability engineering and also a developer of specialized software tools for monitoring and reliability engineering. Our main task in ROMEO Project is the development of an O&M information management platform. And in this talk, I will give you an introduction into the development of this platform. First, I will talk about data integration and why this is an important aspect in this project. And second, I will introduce two of the main concepts for post-processing we have developed in the scope of ROMEO Project. This is the state and event processing system and the system for automated advisory statements. Coming to data integration, we can start from the end and think of what is the task in wind operation in general. We have development where we want to design reliable turbines with a maximum of performance at low costs. We have management where we have financing and planning tasks, and then we have the operation and maintenance phase where we want to control our wind farm, plan maintenance activities, and monitor the turbines. In analytics, we want to understand the behavior of our turbines. So can we improve the performance of the turbines? Can we detect degradation early? And if possible, we want to recommend action early. And then we have energy trade and distribution, where we want to provide a stable electricity supply and also, of course, maximize revenues. Connected to these different tasks, we have a variety of stakeholders. So we have OEM services, the operators, which are mainly active in management and operation, and of course O&M service providers, which actually perform the maintenance work. And in the end, we have grid operators, electricity providers, and authorities caring about trade and distribution. All of these different stakeholders will have a specific demand for information to take decisions in their tasks. And there's a variety of software tools available to support them. So we have monitoring software, workforce planning software, different softwares for condition monitoring and structural health monitoring, and also specialized software for trading and weather forecasting. On the bottom, we have our technical infrastructure, so our turbines producing different kinds of data. Typically, we will have a SCADA system providing time series data and some kind of alarm and event messages and operational state messages. We will also have weather information from the site, and we might have high resolution data for use in CMS systems. And then we typically have data acquisition framework, which gathers all this different data and makes it available for these different tools. So typical situation will look like this. We have a specialized software tool like the CMS system, which will take, for example, high resolution data, produce very specific information for one task in analytics, for example. However, when we talk about decision making in the context of offshore wind operation in a broader sense, we will often have to consider information from different sources. So, for example, if we want to decide about triggering an inspection task on an offshore wind turbine, we will need to consider monitoring data, information from a CMS system. There might be also a result from a prognostic algorithm indicating degradation of a certain component. And we will also have to consider workforce information and weather forecasting. So this is why we think we need to integrate different sources of information to make informed decisions. The setup in ROMEO Project looks quite similar. On the left-hand side, we have the data acquisition infrastructure, which is developed by our partners in the project. And we also have prognostic and diagnostic algorithms for main wind turbine components, which are also developed by the partners in the project. And what we do in ROMEO Project is two things. First, we provide a platform for monitoring and visualization of this data and information already available. And second, we want to combine the available data and information to create useful insights in the form of relevant KPIs and also in the form of our automated advisory process. Coming to the post-processing, one important concept we have developed in the project is the state and event processing system. A bit of background, this is a typical situation we are facing. We have a turbine which is first in normal operation. Then we might have an abnormal process value causing the turbine to behave differently. Later there might be a SCADA alarm which triggers a maintenance process, which itself then has different states. So response time, initial analysis, logistic time, on-site analysis, and repair. And hopefully in the end, the issue is solved and turbine goes back to normal operation. So what we have in general is a system of turbine and process states which are triggered by events. And what we want to have is a system to capture this kind of information and to make it available for further analysis. This might sound trivial in the first place, but the structured capturing and storing of this information is not an easy task to achieve. What we have done in the project is we have looked at different standards which are already in use in the wind industry, which is the OPC Unified Architecture. This is a machine-to-machine communication standard which covers especially conditions of components. And there's the ZOIS standard, which is a standardized coding system for maintenance process states. And based on these different standards, we have derived basic requirements for our state and event processing system. So we want to be able to implement any desired coding system for the determination of states and events. We want to use events to determine state changes. We want to assign information categories to these states. This is particularly important for availability calculation later on. We want to be able to create events automatically based on time series data. We want to derive system states from states of individual components or subsystems. And of course, in the end, the information must be available for further functionality, such as the statistical analysis and availability calculation. So based on these requirements, we can come up with a simple specification. A state describes the condition of a system component or process in a determinable time span. So a state does always have a starting point and an end point, and an event describes an occurrence with some significance at a determinable point in time. So this is important. The state does always have a time span, and an event is just in one point in time. Why is this useful? One important use case is availability calculation and downtime categorization. So if we are able to capture states of subsystems and components based on defined entry and exit events, we are also able to derive an overall system state, which is here state 1, state 2, and so on. And if we have this overall system state, we can assign information categories. We can say state 1 is available, state 2 is unavailable, state 3 is available again, and so on. And then we can do the math and calculate availability in the end, or calculate time fractions of different downtime categories. Now we are able to capture turbine states and events, and also process states and events. And we can think of how we can use this information in an automated process for automated advisory statements. And again, we can take a step back and think of which kind of information do we actually want to provide and which kind of information is helpful. And this has a time dimension. So if we want to provide instant information for maintenance support, we need to provide technical information to service technicians, support inspection and root cause analysis, and provide task descriptions. If we move further in the future, we are in the field of activity planning. So we need to inform about upcoming maintenance events, prioritize and schedule activities, and basically plan maintenance activities and provide technical information as well. If we move even further in the future, we are in the field of strategy planning, where we have questions like defining the maintenance strategy, defining service intervals for individual components. We need to support decisions about service infrastructure, about technical infrastructure needed, and also things like spare part and stock planning. So basic questions we need to answer in the first place are who is the addressee of advisory statements, and what is he supposed to do with the information we provide? So which kind of expertise and knowledge does he have? On which functional level does he operate? And how will he interpret the information provided? Important here is also which kind of decision will he make with the information provided, and can he take this decision directly with the information we provide, or does he need any further information from outside or from his experience? So what we have developed in the project is first a system to formalize different observations in connection to wind turbine operation. So wind turbine operation, we can make different kinds of observations. There might be SCADA alarms coming from the SCADA system. We might have time series threshold functions. In ROMEO project, we have the results of the diagnostic and prognostic algorithms indicating degradation, and we have field inspections from the service technicians. And we have developed a system to formalize these kind of observations and to make them machine readable in an automated process. And how does this process actually look like? It is based on two main entities, which is the reasoning engine and the knowledge base. In the knowledge base, there are root causes and failure modes stored in connection to a set of observations. So what happens is we have a turbine in operation and we make several observations. For example, we have a specific set of observations, which is high failure probability, indicated by a model. We have a SCADA alarm and we have an observation from a field inspection. And the reasoning engine is a logic which takes this specific combination of observations, looks into the knowledge base, and then comes up with an initial diagnosis, but also provides additional information which will directly support the service technicians in narrowing down the diagnosis and perform the maintenance work. What is also important in this process is that we feed back information from the process into the knowledge base, which will over time improve the knowledge base, help to make more accurate advisory statements, and in the end, this will build up a company-wide O&M knowledge base, which is then accessible for all participants, for example, for less experienced service technicians. Summing up, we should start with a clear picture of the task. Think of which data we need to integrate and what is relevant data. We need to establish a system for acquisition of system and component conditions. We need to think of what is helpful information and how to provide it. And then we need to establish an efficient communication and feedback process. Thank you very much for listening to this ROMEO training pill. In case you have any comments or questions, feel free to contact me directly or any of the ROMEO partners, or visit the official ROMEO homepage.